Hey everyone, today we are going to discuss a very important tree topic which is Morris Tree Traversal. We already know, to traverse a binary tree we have several methods. First one is using recursion, the second one is using iterative method. I am not going to go much in details for these two topics, recursion and iterative method. In this lecture, we are going to have a look over this Morris tree traversal because both recursion and iterative method are having time complexity as on and space complexity as on. In the recursive method, we are going to have a recursion stack of n size. In the iterative method, we have to take stack data structure manually to store our recursive calls, maybe our previous pointers. So, so to improve the space complexity, we have introduced this Morris Tree Traversal. So to improve this space complexity to O of 1, we have this Morris Tree Traversal algorithm. So what is this? In the Morris Tree Traversal, we are traversing a tree without using stack or recursion. So we are going to traverse the tree in the O1 with the O1 space and the time is O(n), traversing all the nodes. This is based on a threaded binary tree. In the threaded binary tree, we utilize the right pointer which are null. Let's say in the case of 5, right pointer is null, left pointer is null. So we will utilize this right pointer and point to its successor. Let's say we have to do the in-order traversal of a binary tree. So in this case, if we have this binary tree, so we will utilize the right pointer of 2 which is null. So we will point it to the 1 in order successor, because in order traversal of this is going to be 2, 1 and 3, and in order successor of 2 is 1. So we are going to make a connection from 2 to 1 while moving in the left direction, and while returning from the left direction we will just keep on removing this connection. So in the end we don't have any extra pointer connected. Our tree state is same which is given to us. So now it is based on a threaded binary tree. For every null right pointer, create a link to its in-order successor, processing the data using those links. So we are utilizing these links to achieve our answer. Let's say over this example how we are going to achieve this implementation. So let's say we are starting from 1. So our current pointer is pointing to the root. Now we will see whether there is any left child to 1 or not. If there is any left child, it means we are definitely going to have a in predecessor for the current node. So the fourth, so in this iteration, 2 is predecessor and the 1 is successor of 2. So for 1 we have to find the predecessor. So we will go to the left and the extreme right. So that is definitely going to be the predecessor, because if we are going to do the in-order traversal, we will be processing left subtree first. So if we process the left subtree, it will be 4 to 5. So the left node to the extreme right node, the node is going to be the predecessor. So 5 is the predecessor of 1. So what is the predecessor of 3? 1 is the predecessor of 3 because there is no left subtree of 3. So for 2, what is the predecessor? 4 is the predecessor. So we started from 1 and checked for the predecessor. 5 is the predecessor. We created a link from 5 to 1, and now we move to the left. Remove this current pointer is now pointing to 2. Now for 2 the predecessor is 4. We created a link and moved to the left. Now at 4 the left subtree is null. It means we don't have any left subtree to process. So this is going to be our current node. So if we don't have any left subtree, so the root node will be printed. Let's say we are printing every node in term like for the processing we are just printing. So we will print 4 and now we will move to the right. Now we have already formed this link. Now for the right side of 4 it will go back to 2. 4 is done. The current pointer is again back to 2. Now we will again check for the predecessor whether the predecessor has the connection to 2 or not. So for 2 the predecessor is 4. 4 is already having a link to 2. It means we are returning back from the left subtree after doing processing of all the left elements. So now as we have done the processing of the left subpart, so we can directly remove this connection and print the 2 because it is in order. Left subtree is done for 2 as a root. Now 2 is printed and now after printing 2 we will move to the right of 2. So the right of 2 is 5. Now we will again see whether the left subtree exists or not. For 5 there is no left subtree. So we will print 5 and move to the right of 5. Right of 5 is 1. At 1 we will see what is the predecessor. Predecessor is 5. 5 is already having a connection. So we are returning from left side. It means all the left subtree of 1 is processed and we have to remove this connection. So we will remove this connection and print 1 and move to the right. Okay. From 3, left subpart is null. If the left subpart is null, in the in-order traversal, we can directly print the current node. We are going to print 3 and move to 6. At 6, left subtree is null, so we will print 6 and move to right of 6. Now, the right of 6 is null. So, when our current pointer is becoming null, we are going to break this condition. So this is actually our Morris Tree Traversal. So let's quickly write a code for that. Okay, we are going to write down the in-order traversal using Morris Tree Traversal. So in the Morris Traversal, we are going to have a current pointer tree node. Current is equal to root. We are starting from root. We also need a temporary pointer to reach to our predecessor and making connection to the successor. Temp is null in the starting. Now while current is not equal to null, we will process our elements and in the end we are going to return result which is our list to store all of our items in the tree. Before that we can also have a null check, or maybe later to this. If root is equal to null, we can directly return result. If current is not equal to null, okay, let's say we are at 1. So how many possibilities do we have? Whether there is a left child or there is no left child. If there is a left child, we have to do something with the left child. If current dot left not equal to null, else else means current dot left is null. If current dot left is null, it means we don't have to process any left subtree. We can directly print the current node. It means we can directly add the current node to our answer. Result dot add current dot value, and now we will move further to the right. Current is equal to current dot right. Because left sub part is done, current node is done, we just have to check for the right sub part. Now in case when the left sub part is not null, we have to go to the predecessor. If left sub part is not equal to null, we are definitely going to have a predecessor. So let's say for temp is equal to current dot left, while temp dot next not equal to null. while temp dot next not equal to null, we are going to do the temp equal to temp dot right. Sorry, temp dot right. But there is also one possibility. Uh, if we are moving to the left direction, we will keep on forming the threads, maybe pointers. N- ri- uh, null right pointer to the in-order successor. But while returning from the left subpart, we have to remove those pointers. So there might be case if temp dot right is equal to null, it means we have to form the pointer. If temp dot right, in case temp dot right is equal to current, it means we are returning from the left subpart and we have to discard that pointer or maybe connection from predecessor to successor. Temp dot right is not equal to current. In this case, we just have to move to the temp dot right. So after this loop, we will be at the in order predecessor of the current element. Okay. Now what we have to do is, still there is two possibilities, whether we are going to the left side or we are returning from the left side. If we are going to the left side, if temp dot right equal to null, going to the left side, in the else returning from the left side. Where if temp dot right equal to null, it means we have to form the pointer and move to the left part. Temp dot right equal to current and current equal to current dot left. Now we will have to check for the further left part of the tree. We will check for the current later on. If we are returning from the left side, it means we have processed the left part and now we have to process the current node. We can also discard the pointer. Temp dot right equal to null. Make this link null again and result dot add current dot value and move to the right. Current equal to current dot right. Okay, let's try to submit. Okay, all the temp sample test cases are passed. Hopefully it would submit. Okay, now this problem we have not used any space. We just used this point, we just made these connections and use this connection to process our answer. Okay, let's let's quickly have a dry run over this example as well. Okay, let's start with this example. Our current is starting in the starting pointing to 1. So left subtree is not null. We will get for the predecessor. So predecessor is 2, which is coming from these instructions. So 2 from 2, 2 dot left is already null. So we'll make a link from 2 to 1. Link is formed and current pointer will come to 2. For 2, we will check for the predecessor. Predecessor is 3. From 3 to 2, we will form a link and current will point to 3. At 3, our left subtree is null. It means we are going to print 3, which is adding 3 to our answer. And now moving to the right. Current is at 2. At 2, we will check for the predecessor. Now predecessor dot right is pointing to the current node. It means we are returning from the left subpart. And now what we have to do is we have to remove this link, add to our answer and move to the right. Moving right will take us to the 1. At 1 also, we will check for the predecessor. Predecessor is 2. 2 is already pointing to 1. It means we are coming from left side. Now we have to break this link, print 1 and move to right. So current is now pointing to 4. So at 4, we'll check for the predecessor. Predecessor is 5. link is formed and we are moving to the left. For 5, left subtree is null. We are going to add 5 to our result and now move to the right of 5. Right of 5 is again 4. This point, this is not the current is 4. At 4 we will again see for the predecessor is 5. 5 dot right is pointing to the 4 itself, so it means we are returning from the left part. So we are good to break this bridge and add 4 to our result and move to right. Okay, now our current is at 6. 6 does not have any left part, so we are going to print 6 and move current to right. Now the current is pointing to null. It means we are good to close this iteration, close this while loop. So this is going to be our in-order traversal. 3, 2, 1, 5, 4, 6. Okay, hope you understood the problem. I also have a follow-up question to you. Try to do the pre-order traversal using Morris algorithm. You just have to check for the condition where we are adding our values to the result. So it's going to be pretty simple. Just give it a try. If you are not able to solve that, just comment down below. I will help you out. Thank you. Bye bye.